Okay folks, so the video tonight is, I say tonight because I'm filming it in the evening. That's why the lighting's not great, because if I turn the lights on, it's got there's like hideous reflection and stuff, so I'm going to turn the light off and hopefully it's not so bad. So the video is on alcohols and carboxylic acids, which are the next two homologous series. Hopefully you've already watched the videos on alkanes and then on alkenes. If not, go back and watch those first, otherwise this one won't make a whole lot of sense. So we're going to start off with a quick quiz. So if you can pause the video now and then I'll go through the questions. Like, actually pause it and try it. You'll get more out of this video if you pause it and try it. I know the temptation is when everyone says pause it, you just keep watching. But pause it, quickly try these questions. Okay, so to go through these now. What is a hydrocarbon? I put a little 2 after it because there's 2 marks for this one. It is a compound containing hydrogen and carbon. That's the bit everyone gets right. It's a compound containing hydrogen and carbon only. That does say only, I promise. Right. It's a compound that contains hydrogen and carbon only. Or a compound containing only hydrogen and carbon. Name a homologous series. So the ones that you've come across so far. Alkanes are an example of a homologous series. Alkenes are a different example of a homologous series. And we're going to learn about 2 more today, because alcohols are a homologous series and carboxylic acids are. If you want a quick recap about what homologous series is, they have the same general formula. So if you remember, for alkenes, they were all, alkanes were all CnH 2n plus 2, and they gradually get longer because you're adding in CH2 each time, so they differ from their neighbours by CH2. So same general formula, getting gradually longer. They have the same or very similar chemical properties. They all do the same reactions, and they have very similar physical properties, and the physical properties change as you move along the group. So the shortest alkanes have very low boiling points, and then as the chains of the alkanes get longer, the boiling points gradually increase. Like in fractional distillation, where you've got your fractionating column and you get the shorter chains at the top and long ones at the bottom. So these things are what make a homologous series. Same general formula, they differ from their neighbours by CH2, same chemical properties, and there's a gradual change in physical properties. Right, back to quick quiz. Why are alkenes unsaturated? Because they contain a double bond. In alkenes, there's the carbon-carbon double bond, not an equal sign. That is carbon double bonded to carbon. So they're unsaturated. Saturated means there's only single bonds. Unsaturated, there's a double bond. Right, draw a molecule of propane. So you should hopefully have started to remember by now. MEP-B, methane, ethane, propane, butane. 1, 2, 3. So pro, 3, because it's got 3 carbons. 1, 2, 3. And then ane shows it's an alkane. Alkanes are saturated, they've got only single bonds. So we fill in the hydrogens. H, 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 H. So 3 carbons and then 8 hydrogens. And I've run out of a bit of space to do the final question. But-2-ene. So meth, eth, prop, but, 4 carbons. 1, 2, 3, 4. Ene showing it's a double bond. And then this 2 shows that the double bond has to be on the second carbon. So 1, 2. So we draw the double bond there. And then we fill in the hydrogens. Each carbon has to have 4 bonds. This one's only got 1 at the moment. So it's got 1, 2, 3. That is the oven timer beeping. So we're just going to go and turn it off. And now I'm back. All the interruptions today. Right, so now this carbon's got these 3 hydrogens on it, because now it's got 4 bonds. This one's already got 3 bonds, so I need to draw 1 more. You could draw it underneath, doesn't make any difference. This one's already got 3 bonds, so we need 1 more. And this one's got 1, so we need 3 more. So that is butene. Right. So alcohols. So this is a new functional series, new homologous series, which means it's got a new functional group. The functional group is the thing that defines it as a homologous series. So we knew alkenes, their functional group, if it had a C, double bond C, that made it an alkene. An alcohol is an OH group. Now, it's just a trend in chemistry, I don't know why. We draw an OH for an alcohol as a bond, then an O and a H. What that actually is, we're saying there's a bond with an oxygen and then the oxygen's bonded to the hydrogen. Those two are exactly the same. In this video, I'll probably switch between drawing them both ways, but they are exactly the same thing. So that is the functional group for an alcohol. You guys need to know the first 4 alcohols. So if you remember, meth, eth, prop, bute. So the first alcohol is called, I can't spell, it's called methanol. Methanol. So methanol. So it's got 1 carbon, it's got to have the functional group, so it's got to have the OH, and then remember carbon needs 4 bonds, so it needs 3 more hydrogens. So F, it is ethanol. This is the type of alcohol that's in, this one will kill you. I mean, ethanol will kill you as well, but ethanol is the type of alcohol that's in alcoholic drinks. So ethanol, if you want to quickly pause the video and have a go at drawing all 3 of these actually, ethanol, propanol, butanol. And coming back in 3, 2, 1. Right, hopefully you had a try at drawing them. If you didn't, watch me draw the next 2 and then have a go at drawing the last one. So ethanol's got 2 carbons, 1, 2. We need to have the OH. Doesn't matter where you put the OHs, by the way. So for methanol, could draw the OH up there, H, H, H. Those 2 are exactly the same. So ethanol, 2 carbons, then fill in the rest of the hydrogens. So we've got 4 bonds there, this one's got 4 bonds, it's got the OH on it, so that's ethanol. Propanol, exactly the same, 1 carbon longer. I'm going to rub this out to make myself some more space. 1, 2, 3. Right, technically there's 2 types of propanol. So propanol, so you could have, if you remember from the last video on alkenes, we started talking about numbers in there. If I put the OH there, that is propan 1-ol, because the OH is on the first one. If I move that and put the OH on this one, that is propan 2-ol. And then if I put the OH on the last one, it's not propan 3-ol, we go back to propan 1-ol because we can start numbering them from the other end. So you could have propan 1-ol, propan 2-ol. Actually, whilst you need to know those for the alkenes, you need to know butane, but-2-ene and but-1-ene. For the alcohols, they're happy with you just knowing them as propanol and butanol. So I'll fill in the hydrogens, H, 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 H. I won't sit you make, but there'd be 1 hydrogen on each of those. Do you know what, I will draw them, I don't want you to get confused. Right, H, 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 H. So that's propanol. Technically propan 1-ol, we could put the OH there, and that'd be propan 2-ol. You can put the OH anywhere, it's the same. So for butane, meth, eth, prop, but. Pause it now if you didn't have a go at drawing it earlier, but you've got butanol, so we need another carbon, H, 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 and that's butanol. I could put that OH absolutely anywhere, so actually this is butan 2-ol. If it was on the end, it'd be butan 1-ol. You know, if it was there, butan 1-ol, there, butan 2, there is 2, because we can just start counting from the other end. Whoa, excuse me. Right. So meth, eth, prop, but. So methanol, ethanol, propanol, butanol. So those alcohols, they do catch fire, similar to alkanes and alkenes. That's what a future video is going to be on in terms of one of the reactions. just going to check my quick notes to make sure I haven't missed anything out. So we've got the alcohol. Oh, right. A reaction of alcohols. So I'm just going to, if I draw ethanol, C, O, H. Right. See, I've drawn the bond in there, but that's exactly the same as drawing it as OH. Right. H. So one of the you might be able to hear my children upstairs. They're in the middle of their bedtime, so if you can hear background noise, that's them. So we've got, that is ethanol, and I'm only going to show you it for ethanol, but it does work for any alcohol at all. Is a that's not how you spell D, is a dehydration reaction. Dehydration reaction. And now, just like the clues in the name really, dehydration, if you're dehydrated, you don't have enough water. If we dehydrate an alcohol, we're taking H2O away from it. So if I take away that OH and I take away that H, so they can then come up over here, and it's pretty obvious with a H and an OH we are going to make H2O. So we've made H2O because we have dehydrated it, we have removed water, and then the issue is now this carbon's only got 3 bonds and this carbon has only got 3 bonds, so they form a double bond. So if you do a dehydration reaction, that isn't ethanol anymore, it is now ethene. So for a dehydration reaction, it turns an alcohol into an alkene by removing H2O. I'll just show you one more quick example of that. Obviously we can't do it for methanol because that's only got 1 carbon and there isn't any such thing as methane. Remember, the first alkene was ethene. But if I show you for propanol, so 1, 2, 3, I'll stick the OH in the middle for this one. H. Let's fill in the H's. Okay, so we're going to remove that OH. I'll stick it over here. OH. Doesn't matter which hydrogen we remove as long as it's not that one. So any of the other hydrogens. The reason you can't remove that one is because then these carbons are all fine, but this one hasn't got any to make a double bond with. So you can't take the hydrogen off the same one as you took the OH, but you take one off any of the others. So if I pick that one, so now we've got 2 OHs up here. Sorry, 2. We had OH. We just took another H off, so we've got another H, so HOH, or better known as H2O, water, because we've dehydrated it, and then makes a double bond, because now this one's got 1, 2, 3, 4, and this one's got 1, 2, 3, 4. So we started off with propanol, and we've ended up with propene, so a dehydration reaction. They have crowbarred into the specification a little tiny bit of biology here. So you need to know about fermentation. So fermentation is a way of producing alcohols. So you get a carbohydrate and you use you start with a carbohydrate and you turn it into an alcohol. And how do we do that? We use yeast, a microorganism, and yeast contains enzymes that do this for us. So, example, most alcoholic drinks are made this way, right? So a carbohydrate would be sugar, so you use yeast to turn sugar into ethanol, glucose into ethanol, right? And then, as an example, so wine is made from grapes, so the carbohydrate is the sugar that's in grapes and gets turned into ethanol. Or cider, you've got apples, and it's the carbohydrate is the sugar that's in the apples, and the enzymes in yeast turn it into alcohol. And the name of that reaction is a fermentation reaction. So, that was a lot of stuff about alcohols, and now I'm going to move on to carboxylic acids, which are not as complicated as their name sounds. Carboxylic acids. Again, you need to know the first four. The functional group for carboxylic acids is called a COOH group. COOH. Doesn't make as much sense initially when you look at it like that, but when I write it out, so what that is, you've got a carbon. So remember, carbon has to make 4 bonds, and oxygen has to make 2. Hydrogen needs to make 1. So you've got a carbon. It is double bonded to an oxygen, and then it's got an OH on it. We could also write the OH as O-H. So that bit's very similar to an alcohol, but it's also got the double bond O on it. So this is the carboxylic acid group. We abbreviate that to, when we write it as COOH. So we don't write it as CO2H because it's not a chemical formula. We're just talking about the functional group. The thing that makes a carboxylic acid is having this COOH. And if you look, carbons need to have 4 bonds. This carbon has got 1, 2, 3 bonds, so it would have another bond there, which would either be a hydrogen, if it was the smallest carboxylic acid, or it would be sort of the rest of the long chain. So you need to know the first 4 carboxylic acids. So I'll give you the names. So we've got methanoic acid. So meth means it's got 1, and the anoic acid, 1 carbon. So meth, 1 carbon. Anoic acid tells you it's a carboxylic acid. So we're going to have C, double bond to O, and then on to OH, and then we've got a H. So that is methanoic acid. So what I'd like you to do now is pause the video and try and name the next 4 carboxylic acids. So I'm going to start the video again in 5 seconds. 4, 3, 2, 1. So hopefully you got the next name would have been ethanoic acid. If we're going to draw ethanoic acid, we need a carbon, 2 carbons for eth. Then we have the double bond O, OH, and then this one would just be H, H, H. So that's ethanoic acid. I'd like you to now pause the video again and try and name and draw the next 2. So I'm going to start the video in 5 seconds. 4, 3, 2, 1. I really hope you've paused it and had a go, because it's by testing yourself. Even if you get it wrong, by testing yourself, this is how you help it go into your long-term memory. So we've done methanoic acid, ethanoic acid. So now we've got propanoic acid. Propanoic acid, 1, 2, 3, meth, eth, prop. So we've got to have double bond O and then OH. This one needs 2 hydrogens, and this one needs 3 hydrogens. You could draw that on the other end. If I draw this here, C, 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 we could have double bond O, OH there, and then H, 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 H. These 2 are exactly the same molecule, it's just like a mirror image of them. I tend to draw the carboxylic acids at the right hand side, but that's just force of habit. It doesn't make any difference which end you draw them on. And then the next one is going to be butanoic acid, and butanoic acid, we need another carbon on here, and then that would have the H's on it. Meth, eth, prop, butanoic acid. Right, one reaction of these that I am going to quickly tell you about, and then that's the last part of this video, is the oxidation reaction of them. So oxidation of carboxylic acids. So I'm going to draw you ethanoic acid, C, C, sorry, not oxidation of carboxylic acids, oxidation of alcohols. Right, going back to when we're doing alcohols, and they turn into carboxylic acid, so hopefully it'll make sense to you why I'm doing the alcohol bit now instead of in the alcohol section. So oxidation of alcohols. I'm going to draw ethanol, which, if you remember me saying, was the alcohol that's in alcoholic drinks. And you may have seen this in restaurants back when we were actually allowed to go to restaurants, or if not, you've almost certainly seen it on films or TV shows where people go to a fancy restaurant, they order a bottle of wine, and then the waiter pours out a little tiny bit and gives it to the person to taste. I used to think, because I was very naive, that they were seeing if they liked the wine and being like, oh yeah, I like that, I'll have the whole bottle. But, you know, that could have been a £400 bottle of wine, it's just been opened. If you didn't like it, they're not going to just say, oh, alright, sorry, you don't have to buy it. What you're actually testing is to see if it has been, this is the phrase, if it has been corked, which basically means the wine has gone off because oxygen's gone into it. So the cork in the wine has failed and it's gone off. And the reason I'm talking about that is because that leads to an oxidation reaction. So this is the ethanol, this is the alcohol. If we let oxygen get into it, so remember oxygen is O2, and a different way of writing that would be O double bonded to O. So remember O needs 2 bonds. And then what happens is this splits up, so we have an O and an O, and they both really want to make 2 bonds. And so it robs these 2 hydrogens, so that comes here, H and H, so it's made water, H2O, so I'm just going to rub that out so it's not in our way, H2O. And then this carbon needs 4 bonds and it's only got 2. And this oxygen needs 2 bonds and it hasn't got any. So that oxygen comes over here and then joins them there. And if you look, that's made a carboxylic acid. So we started off with ethanol. And we've turned ethanol into ethanoic acid. And ethanoic acid is vinegar. This is vinegar. Vinegar is the common name for this chemical. So if you taste wine, going back to the restaurant thing, they pour you a little bit of the wine. If it tastes vinegary instead of alcohol-y, then it means the ethanol means oxygen's got in and it's turned the ethanol into ethanoic acid, which has meant it's gone off basically. So oxidation of alcohols, you get alcohol plus oxygen and it turns into carboxylic acid and water. So I've just drawn that for ethanol. I'd like you to have a go at doing that for methanol. So methanol plus oxygen would go to what plus water. I don't just want you to do the balanced equation. I'd like you to have a go at drawing it out as well. So if you want to pause it now, and I'll start again in 5, 2, 1. So you should have had methanol plus oxygen goes to methanoic acid and water. And if I was just drawing that out, so you'd have, here's our methanol, H, H, H. We're going to add H2O, and then what happens is we have, that's terrible, didn't line that up properly. Right, that is our methanoic acid, and it wasn't H2O, it was O2. So we've got that plus O2. Apologies if you got it. So make sure you correct that mistake, and then it turns it into water, because these 2 hydrogens come off, they stick to one of those O's to make the water, and then the other O sticks on there to make the methanoic acid. Okay, so we've got methanol plus that goes to that. And then just to finish, carboxylic acids are acids. They are very weak acids. They're not strong acids. If you remember in the acid course, part of the course we talked about whether they fully dissociate and split up. So this is methanoic acid, and what happens is this H can come off. And so that leaves that one as minus, and it leaves it as H plus. And if you remember, H plus are what makes things acidic. So carboxylic acids will have a low pH. They do behave like acids. So if you add a carboxylic acid to metal, just like acid plus metal goes to salt and hydrogen, if you add metal to a carboxylic acid, you get salt and you get hydrogen. They're just weak acids because, and a quick recap for this, if you add HCl, which is a strong acid, if you put that in a solution, it totally splits up and you get, so if you put 100 HCl's in a solution, you'll have 100 H pluses and 100 Cl minuses. If you put 100 of these in a solution, 100 of methanoic acid, you'll probably get, and I'm making these numbers up to prove my point, but like you'll probably get 99 out of the 100 will stay like this, and only 1 in 100 will split up to do that. It's probably not even 1 in 100, right? You're probably talking it's like 1 in 10,000 or 1 in a million or something like that, but it was more to show my point. Most of them stay together, but a tiny fraction of them will split up, which is why they behave in an acidic way. Hopefully that clears everything.